Hey guys, welcome to a new tutorial. Today we'll be doing a full NumPy crash course that shows you all the essential functions of NumPy. NumPy is the core library for scientific computing in Python, so if you do data science or machine learning, this is a must-know. Now let me give you a small overview what we cover today. I link all those chapters with timestamps in the description below the video, so if you just want to look up a particular use case, feel free to skip to that part. So we'll start with a little NumPy introduction, and after that we jump right to the code and do a hands-on tutorial. So we cover array basics, then we will have a look at the difference between NumPy arrays and Python lists. Then we cover the dot product because this is a very common use case. Then we do a speed test between NumPy arrays and Python lists. Then we cover multidimensional, or also called ND arrays. We see how we can do array indexing and slicing and also Boolean indexing. Then we talk about reshaping and concatenation of arrays. Then we have a look at broadcasting. So broadcasting is a powerful mechanism that allows NumPy to work with arrays of different shape. Then we have a look at different data science functions and access. Then at different data types, at copying arrays, how we can generate arrays, how we can work with random numbers in NumPy. Then we have a look at linear algebra, in specific the NumPy linalg module. For example, we cover eigenvalues and solving linear systems. And as last point, we have a look how we can load data from CSV files into NumPy. Just a small note before we start. If you find this tutorial helpful, please hit the like button and consider subscribing to the channel. This means a lot to me and helps me to continue with such free tutorials for you. Thanks. Let's have a look at NumPy. So NumPy is the core library for scientific computing in Python. So it is essential if you want to do anything with data science, machine learning, or deep learning. And it's also the core package for a lot of the popular machine learning libraries that you might know. For example, it's the core of scikit-learn, matplotlib, pandas, and many more. Now the central object in NumPy is the multidimensional array. So NumPy provides a high performance ND array object that allows operations really fast, and it also provides all the tools for mathematical operations with these arrays. And as a side note, so a lot of the code of NumPy is written in C, and then the Python functions are just wrappers around these C modules. And this is one of the reasons why NumPy is so fast. So here are some of the use cases. So as I said, the central object is the array. So we do a lot of array or matrix operations and linear algebra. Here we see, for example, a 1D array, a 2D array, and a 3D array. And common operations that we do are, for example, the dot product, matrix multiplications, solving linear systems, calculating the inverse or the determinant, then working with eigenvectors and random numbers. And also when we work with images, these are represented as ND arrays a lot of the times. All right, so now enough of the theory. Now let's jump straight to the code. So first of all, if you want to install NumPy, then of course you can do it with pip. So you can do pip install NumPy. Or you can also, if you're working with Anaconda, then you can do conda install NumPy. Both of them work fine. And also if you install libraries like matplotlib or pandas, then this will be installed automatically as well because it's in the requirements. Now let's go to the code. So the first thing we want to do is to, of course, import NumPy, and we say import NumPy SNP. This is just a convention how I think everybody is importing it. And now the first thing that we can do is to check the version. So we can print numpy dot and then underscore version. And now if we run this, then we see 1.19.1. This is at the time of this video the latest version of NumPy. Now let's create an array. So we say a equals NumPy array, and then here we can put in a list. So for example 1, 2, and 3, And now let's print this array. Then we see it down here. So it has only one dimension in this case. And for example, we can analyze this array by saying a.shape. This is a very popular method that we want to check a lot of the times. And this will return a tuple. And here we say it only has one dimension with 3 elements. What we also can check is print array.datatype. And in this case, it can automatically determine the data type. So in this case, it's int64. We will talk about data types in detail more later. For now, let's also have a look at print array number of dimensions. So here, this is only one dimension. Then we can also have a look at the array.size. This will return the total number of elements. So for example, if we have a 4th element, then this will print 4. And as a last thing, we can check the item size. So let's say print a.item size. This will return the size in bytes of each element. So here, as we see, the data type is int64. So each element here has 64 bits or 8 bytes. That's why we see 8 here. And then of course we can access different elements the same as we are doing it with lists. So we can say a and then the index 0. This will print the first element, so the 1. We can of course also access and assign values to elements. So we can say a index 0 equals 10, for example. And then if we print our array again, then we see that the first element is now a 10. Then we can also do mathematical operations, and these work element-wise most of the time. So if we create another array by saying b equals a and then times and then another array, and here let's put in an array of the same size. So let's do 2, 0 and 2, and let's remove this. And then we see all of these elements get multiplied with each other. So 1 times 2, 2 times 0, and 3 times 2. So let's print b. And then we see the result here. So we talk about more of those mathematical operations later. Now let's talk about the difference between Python lists and arrays. So we can create a Python list by saying L equals 1, 2, 3. And we can create a NumPy array by saying NumPy array and then pass in a list. So 1, 2, 3. And now if we print both our list and our NumPy array, then they look the same at first glance, but there are a lot of differences. For example, now let's try adding a element to our list. So we can do this by saying l.append 4. And now if we print our list, then we see it now has 4 elements. So now let's try the same thing with our array, l.append 4. And then this will raise an error. Our NumPy object has no attribute append, so it doesn't work this way. So let's have another way of appending a element. So for our list, we can do L equals our list and then plus another list with 1 item. So this works. So if we run this, then we see again our list has 4 elements. And now let's do the same with our array. So we say a equals a plus, and then let's do NumPy array and a 4. And let's have a look at the result. So now we see our array still has 3 elements, and it's added 4 to each of those elements. So 1 plus 4 is 5, 2 plus 4 is 6, and 3 plus 4 is 7. So this operation works significantly different on arrays. And by the way, this method is called broadcasting, which we'll cover later. So technically correct would be to use an array of the same size. So here 4, 4, 4. This will return the same result, but NumPy is clever enough to also use this and then do it the same way. Now let's have a look at multiplication. So if we say our Python list times equals 2 and print our list, then we see that it repeated our list. And if we do the same with our NumPy array, so a times 2 and print our array again, then we see that it multiplied 2 to each of the elements. So now I think we already get a feeling how mathematical operations work in NumPy. So functions or operations to an array usually operate element-wise. And this is an essential thing that we should know here, that they work element-wise. For example, we can also have a look at other methods. So for example, we can apply the square root to our a and print our a. Then we also see that it applied, so sorry, I have to assign it again, and we print it, and we also see it still has the same size and it applied the root, the square root, to each of the elements. Same, for example, if I say NumPy log, so the logarithmus also operates element-wise. And we will cover these operations more in detail. Now let's have a quick look at the dot product, because it is so popular in data science and machine learning tasks to calculate the dot product of vectors. So let's say we want to do it in Python with our list. What we want to do is, so the dot product is the sum of the products of the corresponding entries. So if we say, let's say we have two lists, L1 and L2 equals another list 4, 5, 6. Now what we have to do is to create a variable to hold the result. So our dot product equals 0 in the beginning. Then we loop over all the arrays. So we say for I in range length L1, for example, and then we do our dot plus equals the multiplication of each corresponding element, so L1 of I times L2 of I, and then if we print the dot, then this works. But this is of course very cumbersome. So in NumPy it's a lot easier. So first of all, we can create two arrays by passing in the list. So we can say L1 and doing the same with L2. And then we can calculate it in one line. So we can say our dot equals NumPy dot and then A1 and A2, and then if we print our dot, then we see we get the same result but a lot faster and with a lot of less code. So this works. And now as a practice, let's do it step by step manually too. So for example, we could also say dot equals A1 times A2. So this works element-wise, so the same as here. And then we can say our dot equals the NumPy sum over this dot. So better let's call it sum here. We can't use sum, so let's just use sum1 and then sum1. And now if we print our dot again, then we see this also gets the correct result. And by the way, all of those methods typically are also instance methods, so we can call them directly on the array object. So we can compute it like this. We can do a1 times a2. This is a array again, and then call dot sum and without an argument. And now if we print this, then this works too. And in newer versions, there's also the syntax to use the @ sign. So if we say a1 and then at a2 and print our dot, then this also creates the dot product. So I think you should remember this syntax because you might see it a lot, and then also this method, of course. And these are just the manual ways that I showed you. So this is how we create the dot product. Now let's do a quick speed test and compare NumPy arrays and lists. And for this I already wrote some code here. So I generate some random numbers. Then I will have the random objects as NumPy arrays and as Python lists. And by the way, you can convert a NumPy array back to a list by calling the list function. And of course, you can also do it the other way around. You can create a NumPy array by creating it from a list. And then I have two different dot product functions. So the one which I just showed you is to do it manually with a for loop, and then do it with our Python lists. And the second one is just to do it in one line with our NumPy arrays. Then we calculate this dot product 1,000 times, and we measure how long it takes with Python lists and how long it takes with NumPy arrays. And then we print both of the times and also the ratio. So let's run it. And then we see list calculation took this long. With NumPy arrays, it only took this long. So NumPy was 138 times faster. So now let's run it again. And again, we see the ratio is 191. So again, a lot of times faster. So this is one thing that you should remember. Working with NumPy arrays and doing mathematical operations usually is a lot faster than with Python lists. All right, so now let's talk about multidimensional arrays or ND arrays. So if we have a array and let's create it by, like we did in the beginning when we only pass in one list. So if we print our A, then we see it only has one row. And if we check the shape, then we see it has only one dimension here. So if we want to have multi-dimensional arrays, we can pass in a list of lists. So we do the first list and then use a second list. And now if we have this and print this, then we see this is a two-dimensional array. And we see now the shape is 2 by 2, and the first number is always the number of rows, and the second one is the number of columns. So if we put in some more elements in here, then this is 2 by 3. So now it has 3 columns. And now if we want to access elements, so if we say A0, this will access the first row. So it will print 1, 2, and 6. Now if you put in another index, so 0, 0, then this will access row 1 and column 1. So it will print the 1. And by the way, there is a shorter syntax, so we can do it with only one bracket and then say our first index, comma, our second index. So this will return 1 as well. Then let's quickly talk about slicing. We will cover this later in more detail. So for example, if you want to have all the rows in column 0, then we can use a colon. So we want all the rows and then only column 0. So this will return 1 and 3. And notice that the result is of rank 1 again. And if we do it the other way around, if you only say 0, so row 0, and then comma, and then colon, then it will print the whole first row. Another typical operation that we can do with ND arrays is to transpose it. So we can say a.t. This will transpose our array. Then we can also calculate the inverse of our array by using the NumPy linalg module. So we say np.linalg.inverse of a. And now I think if I run this, we will get an error because our array must be square. So let's make a square array again. So 2 by 2. And now if we run it, then this works. Then we can also calculate the determinant. So by calling linalg.det, and then this will calculate the determinant of our array. Then we can also calculate the diagonal matrix by calling np.diag of a. And if we pass in an array, then it will return the diagonal elements, so 1 and 4. So this is again a 1D vector. So if we assign this to a variable, c equals this, and then if we pass in a 1D vector to our diag function, then this will return a diagonal matrix where it only puts in these elements and the rest is 0. So this is an overloaded function that can have two different use cases. Now let's talk about slicing again. So I already showed it a little bit. So slicing is similar to Python lists where we can slice our indices. And since arrays may be multidimensional, we must specify a slice for each dimension of the array. So for example, here we have our initial array. And if we want to have only one value, then we can do it by integer array indexing by saying b equals a. And then for each dimension, we put in the integer. So for example, 0 and 1. So in row 0 and column 1. So this will print out the 2. This is how indexing works. And now slicing. Let's put in some more elements. So 1, 2, 3, and also 4. And then here 5, 6, 7, 8. And if we want to have only row 0, then we put in a 0 here for row 0. And then for the next dimension, we use a colon. And this will do from start to end. And of course, we can also put in the start and the stop value. So from 1 to 3, and the last index is excluded. So it only takes index 1 and 2. So these ones. And if we want to have columns, we can do it the other way around. So we can say all the rows and then comma and then the columns we want. So in this case, we want only column 0 or we want only column 1. And we can also use negative indices. So we can start from -1. So -1 and -1. So this will start from the last index. So here we have the last row and the last column. For example, if we put in a 2 here, then we still have the last row and the second last column. So it's the 7. So next to integer indexing, we can also use Boolean indexing. For example, let's create a two-dimensional array, so a list of lists, and here let's use, for example, 1 and 2, and another list 3 and 4, and another list 5 and 6. And now if we print this, then it looks like this, so it's 3 by 2. And now, for example, we can evaluate a Boolean condition by saying, let's say bool index equals a greater 2. And now if we print our bool index, then this has the same shape and contains false or true depending on this condition. So 1 or 2 both are not greater than 2. That's why we see false here. And for all the other elements, it's true. And now if we apply this array to our original array again by indexing it with the bool index, and if we print this, then we see we only get those elements where this is true. So we only get 3, 4, 5, and 6. And notice that this is of rank 1, so it's only a 1D array again. So this is important to remember. And now, of course, instead of doing it in 2 steps, we can also do it in 1 step by simply saying a and then the index where a is greater than 2. This will return the same thing, 3, 4, 5, and 6. And now if we want to have a array that still has the same size, what we can do is we can use the numpy.where method, and then we say where and the condition a greater 2, where this is true, and we still just use the values of a, and otherwise, for example, let's put a -1. And now if we print b, then we see we now have an array of the same shape, and for all those positions where this is not true, we put in a -1. Then we can also use what is so-called fancy indexing, so we can access multiple indices at once. So let's create a NumPy array and put in some numbers. Let's say 10, 19, 30, 41, 50, 61. And now let's print our a first. And now so this will print our array. And now let's create another array just with some indices. So let's say our b equals, and then for example we can also use a Python list, and then NumPy is clever enough to figure this out. So here we can say 1, 3, and 5. And then if we print our a with indices of this list, then we see it only prints those indices, so 19, so index 1, index 3, and index 5. So this is called fancy indexing, and this is actually a common use case in real world code. So a lot of time you have some array and then you want to filter it. And for this, you create some other array and then do some calculations and figure out the indices where this is true and then apply it to the original array. So for example, in this dummy example, let's figure out the even numbers. So we can get the even indices by using a function that is called NumPy argwhere. And then we say a modulo 2 equals 0. So all the even numbers, and then we flatten our array. So this should be only 1D. And then we apply it to our a array. So a and then this new array. Then this will print out all the even numbers. So this is a common use case in real world code. Now let's talk about reshaping arrays. So for example, we can create an array by using the arrange function and then put in 1 and 7. This will create a 1D array with the numbers from 1 to 6. And if we have a look at print a.shape, then we see it's only one dimension with 6 elements. Now we can reshape it by using, let's say, b equals a dot reshape, and then we must put in a tuple. So let's say 2 by 3, and now if we print our b, then we see it now has 2 rows and 3 columns. So if we print b.shape, then we would see a tuple of 2 and 3. And by the way, this will return an error if the shape cannot be used. So for example, if I use 2 by 4, then this will return a value error, cannot reshape of size 6 into shape 2 by 4. So keep that in mind. And we can also do it the other way around, so 3 by 2, then we have 3 rows and 2 columns. Then there's also a method that is called new axis, and this is used to create a new axis in the data, and that's needed, for example, when your machine learning model or your model requires the data to be shaped in a certain manner. And for example, here our shape is only one dimension, and we can add a dimension by saying b equals, and then we use a, and then if we want to add a new axis in the first axis, then we say here NumPy new axis, and then comma, and then a colon. And now if we print b, then we can see a list of lists. So now if we print the shape, then we see this is now of size 1 by 6. And of course we can also do it the other way around. So we can use a colon here and then NumPy new axis. And now if we print the shape, then it's 6 by 1. So now if we print the actual array, we see we have 6 rows and only 1 element in each row. So this is a very useful method if your model requires the data in a certain shape. Now let's talk about concatenation. So in the beginning we saw that in NumPy arrays it's different than with Python lists. We cannot just say plus equals some list, because then it will do element-wise operations. And now if we actually want to append elements, we can still do that, but it's a little bit different. So here let's create a NumPy array, and let's use, for example, again an array of array 1 2 and another one 3 4. And now let's print this first again, and let's say we have a second NumPy array, and this is also a list of lists, and then here use only one list, 5 and 6. And now if we want to put them together, we can say c equals, and then NumPy dot concatenate, and then as a tuple here it needs a and b. And now if we print c, and by default this added it as a new row, so along axis 1, so it has another optional argument axis, and by default this is 0. So if we run this, then this will do the same thing, but we can also, for example, say axis equals none. And then if you have a look at the result, then it's just a flattened 1D array where it appended all those elements. And now if we put in axis equals 1, then this will be a value error because the dimensions do not match. So for this, we could transpose our b. So we say b.t, and then if we run it, then we see now it added the dimensions again and now as another column. So this is one way, and then there's also the h stack and v stack. So for example, let's create two new arrays, a equals numpy array, and then let's say 1, 2, 3, 4, and let's do another one, b equals 5, 6, 7, 8, and now we can use h stack. This will stack the arrays in sequence horizontally, so column wise. So let's say c equals numpy.h stack, and this needs a tuple, so a and b. And now if we print our c, then we see it stacked it horizontally, so one column after the other. And then of course we also have the v stack, so vertically. So if we apply v stack, then it adds the new array as a new row. And yeah, these are the methods how we can concatenate arrays. So now let's talk about broadcasting. So I already showed this in the beginning. And again, broadcasting is a powerful mechanism that allows NumPy to work with arrays of different shapes when performing arithmetic operations. So I think you already noticed that we have to be careful with the correct shapes. Otherwise we will get value errors. And now let's say, for example, we have a large array, numpy.array, and then here we have a list of lists, 1, 2, 3, and another list, let's say 4, 5, 6, and let's copy and paste this. And now let's say we have a new vector, a equals numpy array, and this has only 3 elements, 0, 1, 0, 1. And now we want to add these elements to all the different columns. So technically correct would be that we also have 4 rows here, so like the same shape as here, but NumPy is intelligent in this case. So if we create another vector or another array, y equals x plus a, and if we print our y, then this is working. So now we see it added 1 to this, 0 to this, and 1 to this, and then the same for the next row and for the next, and so on. So this is called broadcasting, and this is very powerful. So in this case we don't need to have all the dimensions like so. So we can omit this, and then NumPy can figure this out for us. Now let's talk about some data science functions and the different axes. So for example, let's create a new array again. So let's say 7, 8, 9, 10, 11, 12, 13, and then another array here. Let's start by 17, 18, 19, 20, 21, 22, 23. And now, for example, let's first again print this. And here we get a type error because here this of course must be a list of lists. So now print this. And now, for example, let's calculate the sum of this. So we can do this by saying a.sum, and this will calculate the overall sum. And as we already seen, we can also use the optional parameter axis. So in this case, none is the default, which will calculate the overall sum, and we can also use axis 0, which will calculate it along the rows. So this means we get one sum entry for each column. So here it will say 7 plus 17, 8 plus 18, 9 plus 19, and so on. And if we do it along axis 1, then it will calculate it along the columns. So we get one sum entry for each row. So now we get two entries. So this is 70 is the sum over these values, and 140 is the sum over these values. So this is also very important to keep in mind. Always be careful which axis you are using. And for example, we can also use the mean. So this will now calculate the mean over all columns. And if we use index 0, then it will do it for each column. And if you use axis none, then it will calculate the overall mean, so only one entry. And for example, some more data science functions are the variance by calling a.var. Then also the standard deviation a.std. And by the way, as I said, you can use this as instant method, or you can use it as NumPy and then std, and then you have to use your array and then axis equals none. This will do the same thing. And of course you also have things like the minimum or the maximum values. So here we see the minimum is 7, the maximum is 23. So these are some helpful functions to do some data science. Now let's have a look at different data types. So if we create a NumPy array and don't specify the data type, then NumPy can figure it out on its own. So for example, now if we print x and print x.data type, then we see this is an int 64 in this case. So an integer with 64 bits or 8 bytes. We can also, for example, if we use a float here, then NumPy automatically knows that this is a float 64. And of course, we can force the data type by passing in the data type as argument. So for example, here we can say data type equals numpy.int64. Then it's still an integer, even though we used float numbers here. And of course, we can also use int 32 when we don't need so many bytes. So then we only have 4 bytes in this case. So I recommend checking out the NumPy documentation to have a look at all the available data types. For example, we can have float 32, float 16, and I think even float 8. Float 8 is not available, but float 16 should be available. So yeah, so this is actually a very common beginner mistake, that you have the wrong data type in your array, and then your model assumes another data type, and then it will raise a value error. So if you want to fix that error, just pass in the correct data type. And a lot of times I think float 64 or float 32 should be good for your model. Now let's talk about copying arrays. So here we have to be careful. Let's say we have an array with some numbers 1, 2, and 3. And now if you make a copy by saying b equals a, and then if we modify b by saying b index 0 equals 42. Now if we print b, then the first entry has 42. But now if we also print A, then you might be surprised because A also has 42 as first value. And this is because here we only copied the reference, and now both objects still point to the same location in the memory. And this is why it modifies both arrays here. So we have to really be careful in this case. So if we want to have an actual copy, then we can say a.copy. And now if we print B and A, then we see that A is still the same as in the beginning. Now let's talk about generating data or generating arrays. So there are some methods to initialize arrays. So for example, very popular is to use NumPy zeros and then as a tuple the size, let's say 2 by 3. And now if you print our A, then this is an array full of zeros with this shape. Then of course there's also NumPy ones, which is doing the same thing but filling it only with ones. And as you might notice, the default data type here is a float. So let's print a.datatype. Then we see this is a float 64. Now if you want to have specific values, we can do this by saying a equals NumPy full and then the shape 2 by 3 and then the value, let's say 5.0. And now if we print this, we have an array of this shape all filled with 5s. Then we can get the identity matrix by calling numpy.I, and this only gets the shape. So this will create the identity matrix. Sorry, this only gets one argument. So let's say 3, and then it will return a 3 by 3 matrix where the diagonal is filled with ones and the rest is 0. Then we also already have seen the arrange method. So NumPy arrange and then a number. So now if you print our A, this will be a one-dimensional array from 0 to 19. And what's also helpful is the so-called linspace function. So linspace, this will get the start and the stop and then the number of steps. So now this includes, if we have a look, it is this array. So this includes the start value as first entry and then the stop value as last entry, and then makes sure that we get 5 elements. So all of those numbers in between are equally spaced. So NumPy linspace is a very handy method if you need to create equally spaced arrays. Now let's talk about random numbers. So we can also generate arrays filled with random numbers by using numpy.random random, and then we need a tuple as the size. And now this will generate an array with random numbers from the uniform distribution, so between 0 and 1. Then there's also the so-called Gaussian or normal distribution. So here we have mean 1 and 0 variance. So we get this by calling NumPy random rands n. And now here we have to be careful because this doesn't take a tuple as shape, but each dimension as a separate argument. So here we have to be careful. So this is the normal or Gaussian distribution. For example, if we generate a 1D array, so with a lot of elements, and then print a.mean and a.variance, then we see this is almost 0 and variance almost 1. Then there's also a function to generate random integers. So we get this by using NP random and then rand int. And here we can use the start and the stop value. And then a size equals a tuple, let's say 3 by 3. And now if we print A, then A has size 3 by 3 and random integers between 3 and 9. And the 10 is excluded. So if we put in two numbers, then it has the lower and the upper bound. And if we only put in one number, then it uses 0 as the lower bound and 10 as the upper bound. So now here we see it also has 0 or 2 in it. Then when we want to get a random choice, we can get this by saying A equals NumPy random choice and then an integer and a size equals, let's only use 10. And now if we print our A, then we see it generates an array with this size and randomly chooses elements between 0 and this number. So we can use it with a single integer parameter here, but we can also use it with a list. So let's say, for example, -8, -7, and -6. Then it randomly takes elements from these possible values. And now if we print our A, then it might look like this. Now let's talk a little bit more about the linalg module. So for example, how we calculate eigenvalues with this. So eigenvalues are, for example, needed if you do machine learning and apply the PCA algorithm or principal component analysis. So let's create a new array and let's use a list of lists 1 and 2 and 3 and 4. And then we get the eigenvalues and the eigenvectors by calling the linalg.eig function and passing in A. So if we print the eigenvalues, then we see we get the two eigenvalues because this is a 2 by 2 matrix. And now if we print the eigenvectors, then we see we get two eigenvectors. And here we have to be careful because this is a column vector. This means that column 0 corresponds to the eigenvalue 0. So we can verify this by using the equation the eigenvector times the eigenvalue equals a matrix times the eigenvector. This is the definition of eigenvalues. So now if we say our first one, let's say B equals, and then we use eigenvectors, and now we know this is a column vector. So we want to have all the rows and only column 0. And then times the first eigenvector, so eigenvalues of 0. Now if we print this, then we see this result. And this should be the same as if we copy this and multiply our eigenvector with our array, and we multiply this, and we learned in the beginning we can use the @ sign. So now if we print B again, then this is incorrect because we have to do it the other way around. Sorry about that. So we have to do it this way. And then we see this is the same result. And by the way, we can verify this by using, let's call this C. And now if we print B equals C, then we get true and false. So this is surprising because we see these have the same values if it's printed. So, and now if we evaluate it like this, then it evaluates each dimension separately. And here we run into some numerical issues. So this is actually not the correct way to compare it. So to compare the values, what we actually want to call is numpy.allClose, and then we use B and C. So now if we print this, then this returns true. So this is also very useful to know when we want to compare two arrays. If they are equal, then use the NumPy allClose function. Now let's talk about solving linear systems, and let's use a real world example. So the question is, the admission fee at a small fair is $1.50 for children and $4 for adults. On a certain day, 2,200 people enter the fair and $5,050 is collected. And now the question is, how many children and how many adults attended? So this is a typically linear system where we have two unknowns, and we also can make two equations. So we can say x1 plus x2 equals 2,200. And then we also can say 0.5 times x1 plus 4 times x2 equals 5,050. So x2 is the number of adults and x1 is the number of children. So we can also write this in mathematical formulation. So here our x, the unknown, equals a vector x1 and x2. Then our A, our matrix or ND array, has the entries 1 and 1. So here 1 and 1. And then in the second row 0.5 and 4. And then our B equals the result 2,200 and 5,050. So now if we write this as a linear system, then we have the formula A times X equals B. And now if we want to solve this for X, then we have to compute the inverse of A, which I already showed you what we can do with the linalg module. So the inverse of A times B. So this is how we can solve it. So now if we jump back to the code and do this manually. So first let me show you the manual way, and then let me show you another method which is better. So first let's create our array A equals NumPy array, and then if you remember, a list of lists, and in the first row we have 1 and 1, and in the second one we have 1.5 and 4.0. This is our A, and our B equals, and then NumPy array, and then only one dimension, and here we put in 2,200 and 5,050. So now we can say our X equals the inverse of A times B. So we say numpy.linalg.inf of A, and then times B, so the dot product with B. And now if we print X, then this is a small x. And now if we print X, then we see the result. And if you double check the math, then you see this is correct. But actually, this is not the best way to solve it, because using the inverse is actually, it's a little bit slow, and it's also not perfect, because then you run into some numerical issues. So a better way is to use the NumPy linarg solve function. So here we say x equals NumPy linarg dot solve, and then a and b, and then if we print our x, then this has the same result, but this is the preferred way. And now you see it's that simple to solve linear equations. You just have to be careful to create the correct arrays a and b, and then you apply this function and get the result. Now, as a last thing, let's talk about how we can load data from CSV files into NumPy arrays. And for this, I have a file in the same folder. This is the popular spam-based data set. And basically, there are two functions that we can use in NumPy. This is NumPy load txt and NumPy gen from txt. So both are similar and both usually work fine. I prefer the later one because it offers a little bit more options for your parameters. But basically what you have to do is we have to say data equals, and then we can say NumPy load txt, and then the file name. So this is called spambase.csv. Then we also have to use the delimiter, which in this case is a comma. So we use a string and then a comma. And then it's also good practice to also already include the data type. So here we say data type equals numpy.float32. And then this should work. So now we see if we print the data, then this will print the large array. So let's only print data.shape, and then we should see the shape of this array. So this is working, and the same with numpy.gen from text. Then we also get the same shape, so both methods are fine. If you want to have a more detailed look into these functions, then I have a whole tutorial about loading data. And I will link it in the description so you can check it out. But basically, you can use these functions and then you can, for example, start applying them to your machine learning model and doing your training. So yeah, that's all I wanted to show you for NumPy. These are all the essential functions, or most of them, that you should know. And if you want to learn more, then I always recommend to check out the official documentation. There you find even more useful methods. But for now, I think we covered a lot, and you should be ready to go and to work with NumPy. And yeah, I hope you enjoyed this tutorial. If you enjoyed it, then please hit the like button and subscribe to the channel, and see you next time. Bye.